Hello and welcome. In this video, we are going to learn the concepts of the particle swarm optimization algorithm. This algorithm is one of the most well-regarded algorithms in the literature of optimization and has been widely used in a variety of fields in both science and industry. So I've been using this technique for many years, and that's one of my favorite algorithms in the literature of optimization algorithm. So we're going to be talking about the structure of this algorithm, the first inspiration, the structure of this algorithm, and its mathematical equations. We are going to also do a bit of experiments to see how the impact of the controlling parameters on the performance of this optimization algorithm. Alright, so let's start with the inspiration. The particle swarm optimization algorithm mimics the navigation and foraging of a flock of birds or school of fishes. Before we see the mathematical model of PSO, let's go back to our analogy. Here's the mountainous region and the team is about to start the search. The badge team decides to use the PSO technique to look for the treasure. So what do they have to do? They have to, of course, follow the PSO rules. Okay? To show how they move, we need to look at them from the top. Okay? So I'm going to visualize how they move in the mountainous region. So here's a contour map of the region, and we assume that the treasure is on the valley on the right-hand side. Okay, as you can see here. So to use the PSO algorithm, Bob, Anthony, and Jennifer should follow these rules. Rule number 1, each team member needs to record the deepest valley visited so far, which is the location with the minimum elevation, or Z. Now rule number 2, before any movement, they need to communicate to be able to find out and update the deepest valley that the entire team has found so far. Okay? So in the first rule, they try to save and keep and record the best value that they have found so far. But in the second room, they try to find and update the best position that the entire team has found so far. And finally, in the rule number 3, each team member knows his or her current travel direction. So they have different directions, so they might start with a random direction or not, it depends. But they need to know their current direction because they're going to use it to be able to find the next location. To move, every day each team member walks 10 kilometers towards the current movement direction, 10 kilometers towards the personal best location, and 10 kilometers towards the team's best location. So here's an example that shows how every team member relocates. So the blue arrow shows the direction towards the team best location. The red arrow shows the direction towards the personal location, and the yellow arrow shows the current direction. So as the team agreed, Bob needs to walk 10 kilometers towards the current direction, 10 kilometers towards the personal base, and 10 kilometers towards the team's base. So this will be Bob's new position after a long day and 30-kilometer hiking. He can now finish the day and get some rest. So the new position now might be better or worse than the best value found by Bob or the entire team. If it is better than the personal best, Bob needs to update his record before he goes to bed. However, if it is better than the team's best location, he needs to update his record again and inform the rest of the team. If the new location is not better, Bob doesn't need to take any actions. We assume that there is no improvement at this stage, so Bob can go to bed. Now, this is the next day, so he wakes up and now he has to, of course, find the direction towards the team best location, the personal best location, and he knows current direction. So we update the arrows. You see the blue, red, and yellow arrows. So he needs to walk again 10K towards the current direction, 10K is personal best, and 10K team's best location. Okay, so this is the path that he will travel by the end of the second day. So this is the path that he has traveled so far. If we continue, here's how the path looks like after 5 days. Day number 3, day number 4, and day number 5. So now the question is, what makes the PSO a stochastic algorithm? Remember that we assume every team member moves 10 km every day? We can vary this by a random component. 2 times random times 10 km, where r is a random number in the interval of 0 and 1. So this random component varies the walking distance from 0 to 20 km. And this impacts the next location every day. Here's an example. This is where Bob sleeps after traveling exactly 10 km. If the random component gives 1 3 times, the position is different. So here's where Bob sleeps when walking 20 km in each direction instead of 10 km. So depending on the value of r, he might end up somewhere in this area. We have now some sort of random search, okay, because he can sleep anywhere in the green shaded area. This is the area for day number 1. Depending on where he sleeps in day 1, the shape of the next area will be different, since all the directions are calculated based on the current position. If we assume that Bob sleeps where the first arrow stops, the next day Bob will camp somewhere in this area. And here's the area that he might sleep in day 3, day 4, and day 5. Note that this figure shows the areas around each camping point where traveling 10 km in each direction. Therefore, the possible area to search is much wider than what you see in here, because the walking distance might be any number between 0 to 20 kilometers. Also, Bob is not alone. We have Anthony and Jennifer in the team who also follow the same rules. The personal best and team-based solutions are updated at the end of every day as well. Therefore, the search area changes depending on the best locations found so far, as well as the random component. Now, the main question is, how does this stochastic process guarantee finding the treasure? Generally speaking, because the team maintains the best locations in the region and search around them, the possibility of finding a better location is really high. You can see in this figure that at some point the team is going to find the deepest valley. Or at least the team is very likely to find the treasure. To slow down the search process, each team member might reduce the distance they travel daily to be able to locally search around the interested region. A wise idea might be to reduce the walking distance proportional to the number of days in the expedition. Here's an example. This figure shows that the search area becomes smaller and the search process becomes local rather than global every day. This is exactly how the PSO algorithm performs search. Now you know the concept of PSO, let's learn its mathematical model. We are going to first start with a mathematical model of our analogy, and then we will look at the formal equations of the particle swarm optimization algorithm. Each team member defines its position by a pair of x and y. We can store them in a vector called x, it's a capital X. So x1d shows the location of the first team member in the day d. To write a general form, we might replace 1 by I to be able to show the position vector of the ith team member. Also, to be able to move in an n-dimensional search space, we can add more variables in the vector x, as you can see here. To update the position vector, we need to define the movement direction and speed. This can be done using a vector called velocity. The v vector on the left-hand side of this equal sign shows the velocity in the next day. This vector is defined by 3 components: current velocity, tendency towards the personal best, and tendency towards the team's best, which we are going to call G best from now on. For the second and third components, we need to calculate the distance to the personal best and the distance to the global best. Each component is multiplied by 2 times r to randomly increase or decrease its impact. So this is where each component is. With calculating the velocity of the next day, the position can be calculated as well. This is how we can easily read this equation. The next day's position is equal to today's position plus the velocity for the next day. Remember that we use the velocity in the current day to calculate the position in the next day. In the PSO algorithm, every solution of a given problem is considered as a particle, which is able to move in a search landscape. In order to update the position of each particle, two vectors are considered, position vector and a velocity vector. The position vector shows the position of the particle in the landscape, and the velocity shows the direction and intensity of movement. These two vectors are updated in each iteration with these two equations. There are slight changes compared to the mathematical model in our analogy. Firstly, instead of d, we have t, which stands for iteration. Secondly, the current velocity is multiplied by a variable called inertia. And finally, we have c1 and c2 for the last two components in the velocity vector. There are also different terms for each component of the velocity vector. The first term is called inertia, since it maintains the current velocity. It maintains the current direction, the movement direction. The second component is called cognitive component, or some people call it individual component. This is because each particle is considered the distance between its personal base and the current location. So that is why it is called the individual component. The last component, however, is called social component, because the particle calculates the distance between its current position and the best position found by the entire swarm. It is worth mentioning here that for the variable g in the social component, there is no subscript, because we have just one best solution in the swarm for all particles. The impact of cognitive and social components on the movement of particles can be changed by tuning the coefficient c1 and c2. You might be asking now, how about the initial weight? What does this parameter do? This parameter tunes exploration and exploitation. It is normally decreased linearly from 0.9 to 0.4 or 0.2 sometimes. This corresponds to the distance that Bob, Anthony, and Jennifer travels every day. If you remember, we concluded that to find the treasure, they need to slow down the search. Here in PSO, the exploration is increased and exploitation is decreased proportional to the number of iterations for the same reason. Here's the pseudocode of the PSO algorithm. The algorithm starts with initializing the controlling parameters. We can then initialize the population of the particles, and we have a main loop. In the main loop, we need to first calculate the objective for each particle to be able to update the p-best and g-best. After calculating the objective p-best and g-best, we can then update the velocity and position vectors for each particle. And at the end of this loop, we can return g-best as the best approximation for the global optimum. Alright, let's do some experiments now with the particle swarm optimization algorithm. You can see on the right hand side that we have 121 particles. We're going to require these particles to find the global optimum for a test function over the course of 500 iterations. C1 and C2 are both equal to 2, and the initial weight linearly decreases from 0.9 to 0.4. We will assume that the global optimum is on my hand. Okay, so we're going to see how the particle swarm optimization algorithm find the global optimum on my hand. Okay, so ready to run this code or run the particle swarm optimization? Here we go. We'll probably need to wait 10 to 20 seconds, but let's start now. Well, you see the search process or the exploration linearly or gradually decreases, and now the particles all scattered around my palm. And now if you wait a little bit more, they will converge towards the global optimum, which is right in the middle of my palm. Do you see that? A few more left. There we go. Just one more left. Come on. And there we go. Okay? So did you see that? I purposely distributed all particles around a grid to see how they move. There were also vectors coming from each particle to show the intensity and the direction of the movement. Let's do some more experiments now to see the impact of the controlling parameters on the performance of the particle swarm optimization algorithm. In all experiments, we'll be using this test function now. It is a multimodal test function, and the global optimum is located at the origin. In this experiment, the initial weight is changed. In the left figure, the initial weight is 0. In the middle figure, it linearly changes from 0.9 to 0.4. And in the right figure, the initial weight is always equal to 1. Let's run this experiment to see how the particles move. It was observed that the acceleration was at the lowest level when the inertia is equal to 0. And the acceleration was at the maximal level when the inertia was equal to 1. However, changing the inertia parameter during optimization will balance acceleration and exploitation, which is a very, very helpful mechanism when searching for the unknown global optimum of a real-world problem. In the last experiment, we are going to find out the impact of C1 and C2 on the performance of the particle swarm optimization algorithm. On this side, we are going to run the PSO with C1 equals to 0 but C2 equals to 1. That means there is no individual component and every particle follows the best solution obtained so far. On this side, however, C1 is equal to 2 but C2 is equal to 0. That means every particle searches one part of the search landscape. There is no information exchange between the particles because they don't need to know where the global best is. So let's run this experiment and we'll see how the particle search and move around the search space. Okay, so here we go. So as you can see on this side, the particles quickly converge towards the global optimum, and now, it might be a local optimum, but basically they converge towards a point, and now they locally search around it. But on this side, every particle is working or is searching one part of the landscape, and there is no convergence at all. They don't converge towards one solution. So this side is where the exploration is at the lowest level, but the exploitation is at the highest level. This side, the exploration is at the highest level, but the exploitation is at the lowest level. So you see, with balancing C1 and C2, you can balance exploration and exploitation as well. So the initial weight is not the only variable or parameter to change the exploration and exploitation. Okay, but honestly, the impact of the initial weight is more significant than the impact of C1 and C2. So yeah, that's probably everything for this video. So I hope you enjoyed the experiments and everything, and I will see you in the next one.